there is a law called Hooke's law, which is defined as restoring force is directly proportional to x, that is displacement. More and more restoring force, the restoring force is always directly towards the mean position, and displacement is always measured from the mean position. So more and more restoring force, to get more and more restoring force, you have to put more and more mass. That means you have to push or you pull it more and more. So that more restoring force, more displacement. That's very nice. And there is a proportionality, should be replaced by a constant. That constant is called spring constant. And also I have to put a negative sign. This indicates that the restoring force and the displacement are opposite to each other. So this spring constant having a dimension Newton per meter, that's just a unit, the force per displacement. Now what I'm going to do is I'm going to calculate this time period of the spring for the time. So I will be having a spring and I have attached a mass over here of certain mass m, and this mass is at equilibrium position, and I have to give a little push or pull so that I can make that guy to oscillate up and down and front and back motion. That oscillation is nothing but simple harmonic motion. So now, this is a restoring force formula, and you know that when there is a simple harmonic motion, acceleration of the simple harmonic oscillator is given by minus omega square x, where omega is equal to angular frequency, which is square root of k by m, where m is a mass suspended, k is a spring constant of the spring, and omega is an angular frequency. So because of the mass suspended, there is a restoring force, and because of the restoring force you have an acceleration. That acceleration which is given by minus omega square x, because this spring executes simple harmonic motion. So that's why I have a minus omega square x. That's why, so because of this mass I can have acceleration which is a, so which will give you the force F m a. What is a? A is here minus omega square x. And this restoring force leads to an acceleration. So I don't have any problem in comparing these two guys. And that's why I'm going to compare minus kx is equal to minus m omega square x, where x is displacement. So I can cancel each other. So minus also disappear. I am left with omega square is equal to k by m. This implies omega is equal to square root of k by m, where k is a spring constant, m is a mass attached to the spring, and omega is angular frequency. And I can write angular frequency in terms of time period, which is omega is equal to 2 pi by t, which is time period. So I'm going to write as 2 pi by t, which is equal to square root of k by m. I want to have an expression for time period of the spring that t is equal to 2 pi square root of m by k. So I'm going to write it again here. Is time period of the simple, is a spring is equal to 2 pi square root of m by k, where m is a mass suspended to the spring and k is a spring constant of spring. Now here it is a spring. I have put some mass over here, I suspended some mass. Because of this mass, I can have an oscillation. And I have to push it or pull so that I can make it to oscillate front and back. So here I am going to do it. So there is a front and back motion. So the time period is the time taken for one full complete oscillation. So if you start from here, going to the bottom, coming to the same point. So whatever the time taken for the one full oscillation, that time is equal to the time period of the spring, which is given by 2 pi square root of m by k. So now question comes. On what factors this time period depends? However, this equation says, hello, time period depends on the mass. And this equation says, hello, there's a time period depends on the spring constant. So my question is again, does it matter that if I move the spring from the mean position to a very little, next time I'm going to move it for a very far? Does it make any sense? Does it make any difference for the time period? No. As soon as Hooke's law varies, the time period is independent of the amplitude. It doesn't matter from how far you take the mass from the equilibrium position. As soon as the Hooke's law varies. On what factors the time period depends? So T depends on the mass suspended. So here is a mass which is suspended. So more and more mass you suspend, more and more time period you get. That means the time taken for every oscillation is more if you increase the mass suspended. That's fine. And however, another side, I have time period which is inversely proportional to square root of k. K is a spring constant. So it's a measure of, so see here, spring constant is a measure of force per displacement. So spring constant is a measure of force per displacement. So more and more spring constant, less time period. So when can you make it more spring constant? Only when the axis is small. The axis is a displacement. For the constant force, if the displacement is less, then I can say that spring constant is more. That means the spring has to be very stiff. So the spring constant is more for the stiff springs, and if the spring constant is more, time period has to be less. So if the spring is very stiff, the time taken for the spring to oscillate is very less. That's how it relates. Now, oh my God, I am having T over here, time period, and I don't find any expression I don't find any term like the G, which is a gravitational acceleration. That means, if I take my spring system to moon, if I take my spring system to outer space where there is no gravity exists, it doesn't matter where I take, the time period of oscillation is independent of the gravitational acceleration. That's why there is no dependence on G of T. Now, I'm going to discuss what is time period for simple pendulum. I've discussed what is the time period for the spring, which is dependence on the mass of the spring, mass which is attached to the spring and the spring constant. Now, what is the time period of the simple pendulum? How the simple pendulum looks like? There is again a rigid support and a wire or a string which should be massless. And ideally I'm talking it's a massless, but generally the mass of the string is very, very less, so that I can neglect the mass of the spring. And there's a very beautiful bob over here of certain mass m, which is actually point mass ideally talking, or else it should be very less. And this mass is made to oscillate front and back, so that mass, that is a simple pendulum which is executing simple harmonic motion. So here it is, a simple pendulum. One end of the string is fixed, point of suspension, and this is actually the top of the bob, and which the bob is here of certain mass m, which is made to oscillate front and back. Now it is executing simple harmonic motion. Let me say, L is the length of the string, m is a mass of the string. So I measure L. Remember, I have to have a string which is inextensible, so the length should not be varying for the time being. And length is here, mass over here, with mass of the bob, and this pendulum is making simple harmonic oscillation, front and back. Let me say, after a certain time, the bob is here, with angular displacement theta. So let me say x is a displacement from the mean position to the extreme position. This is mean position. So after a certain time, the bob is over here with the displacement x, with the angular displacement theta, and L is the length of the string. Now, so my question is, at the mean position, what are the forces acting on the bob? Oh, very nice. One side, I have a string, so that I can expect a tension force acting on the spring. So that tension is this. And there is another force acting on the mass, Bob young, which is nothing but gravitational force, that is weight, which is mass of the bob times the gravitational acceleration. So I will give a little push or pull so that this bob oscillates front and back, which executes simple harmonic motion. Now, when the bob is here, after a certain time, the angular displacement theta, what are the forces acting on the bob? See, there is again a tension acting on the string, which is actually along the string T, and again there is a gravitational force, which is nothing but weight, which is acting exactly downward, which is young G. Exactly downward. What I am going to do is, if this is theta, this should be T. So I am going to resolve this young G, which is gravitational force weight, into two components. One is horizontal component, that is nothing but young G cos theta, which is horizontal component. Another one is young G sin theta, which is a vertical component. So what I have done, I have resolved this young G, which is weight, into two components. One is horizontal component young G cos theta and vertical component young G sin theta. And there is something surprise here. So this tension and the horizontal component of young G, which is nothing but young G cos theta, do balance each other, and there is a net force acting on this line, which is equal to 0. So that's why the tension is balanced with the horizontal component of the weight young G. And what makes this bob to oscillate? There's only one vertical component, which is young G sin theta, which makes this bob to oscillate, which is nothing but the restoring force. So the restoring force, which is responsible for this bob to oscillate front and back, that is given by young G sin theta. There is no surprise that to put negative sign, because force is always opposite to displacement, minus young G sin theta. I make an experiment for the very small angle theta. I'm not going to allow this bob to oscillate for the very large angle theta. Very small angle. So that if the theta, so that angle, now I'm going to tell you something about small angle approximation. So very, very simple. If this theta is very small, I'm not going to allow this bob to move for a very large angle theta. And if the theta is very small, what happens is sine of theta is very approximately to theta. There is no actually change if you take the sine of theta and theta. So this is called very small angle approximation. I'm going to write for expression and for restoring force, which is minus young G sine theta. I'm going to put as theta. Let me say this is equation number 1. Now, I told you the last time also, for the spring, the restoring force makes mass to oscillate up and down, which is executing simple harmonic motion. So the acceleration of the simple harmonic motion is given by, oscillator is given by minus omega square x, where omega is a angular frequency, x is a displacement from the mean position. So there is again a force, which is mass times acceleration, which is mass times acceleration of the simple harmonic oscillator, nothing but minus omega square x. So let me say this is equation number 2. So left hand side, force, restoring force, which gives an acceleration of minus omega square x. So I don't have any problem in comparing these two. So I'm going to comparing equation 1 and equation 2. So I'm going to compare these two. So minus young G theta is equal to minus young omega square x. So that is something I can tell you. This is theta, this is x, and this is the length of the string. There is a relation. Theta is equal to this arc length by length of the string. So if I take this as the radius of the circle, and this is an arc of the circle, so I have to extend this circular path so that I can write this angle theta as x by L. This is what the relation says. Now minus minus disappear, and also I don't have any problem with this 2m. Left is g theta is x by L, as I told here, is equal to omega square x. I lose my x here, both sides same, so omega square is equal to g by L. Omega is equal to square root of g by L, where omega is angular frequency, g is the gravitational acceleration, and L is the length of the string. So I want to have an expression for the time period of simple pendulum. So I have to write this omega in terms of time period, 2 pi by t is equal to square root of g by L. I want to have expression for t, which is 2 pi times square root of L by g. One of the wonderful equations in physics, which is time period for simple pendulum, which is 2 pi square root of L by g. Now what matters? Whether the time period depends on the amplitude, does it matter if I move this bob from here or here or here? No problem. For any amplitude, measure should be less than 20. So if the amplitude is varied, the time period doesn't change at all. So that t is independent of amplitude. It doesn't matter from how far I take this mass from the main position. That's what it is. So on what factors this time period depends? Time period of the simple pendulum depends. As the equation says, hello, time period depends on the length. Okay, the length of the string. And also there is the time period depends on the g, that's the gravitational acceleration. The last time I told you, if I take spring to the moon or any other outer space, time period doesn't change because there was no g in my equation. This time I have got g over here. So the gravitational acceleration depends. So how? That is inversely proportional to square root of g. If I take my simple pendulum system to the moon, where the gravitational acceleration is less, 1 by 6 times of gravitational acceleration on Earth's surface, and the time period is inversely proportional to g. G on moon is less, t has to be more. That is, time taken to complete one oscillation is more if you do experiment on moon. If g is equal to 0, when can you make it? There is a possibility if you go deep into the earth, at the center of the earth, g is equal to 0. If g is equal to 0, t is infinity because it is here. So t infinity, that means time period is infinity. So the time taken for one oscillation is infinity. That means the time is simple pendulum doesn't oscillate at all. Okay, fine. Now, what is the dependence on the length? It's here, the square root of L. If you increase the length of the string, the time period also increases. So there is one possibility of increasing the length. I have to just heat, or I have to increase the temperature of the medium so that the length of the string can be expanded or can be extended, so the time period also increases. And if I increase the length for 4 times, this is increased for the 4th time. The time period is increased for 2 times because square root of 4 is 2. So it is told that the time period is directly proportional to length. If I increase the length, time period also gets increased. And what is any other fact? Okay, there is something called I can confuse you now. You may not believe it. I feel very difficult to convince you that the mass of the bob over here is independent of the time period. So time period doesn't depend on the mass. Whatever the mass you suspend. Either you suspend an elephant or an ant, it doesn't matter. The time period remains constant. Yes, the last time I had an expression for the time period of a spring, which is 2 pi square root of m by k. So there was a dependence on mass. Now the question comes, does the time period of the simple pendulum depend on mass? It's very easy to infer that there is no mass term, so there is no dependence on mass of a time period. So that is, time period is independent of mass. It's very difficult to convince. If I hang an elephant one side, another side if I hang an ant for the same length of the string, the time period, you may think the time period may vary, but it is not so, unless the spring doesn't break. Now, I am going to convince you that the time period is independent of mass for the same length and the same g. So that's why I got here two systems, time spring here, this is simple pendulum, another side I also got simple pendulum. What I've got is, I've got the same length of string, that is 0.5, that is half of the meter, this side also half of the meter. But what I do is, I just change the mass. This is of 50 gram and this is of 100 gram, double of this. So I'm going to measure what is the time period for this 50 gram, what is the time period for that 100 gram. So before that, this is not so easy to make you believe physics. There is something which is great here. So this is, I'm going to predict first by the equation, which is a beautiful equation I got in terms of length and gravity. I'm going to predict first theoretically what is the time period for one oscillation. As I said, the length is 0.5. I got the equation over here. Length is fixed as 0.5 and g is taken as constant, which is 9.8 meter per second square. And if you calculate this mathematics, you'll get 1.418 seconds, which is theoretically predicted value of time period. So I want to convince you that the experimental value for the 50 gram pendulum and also 100 gram pendulum are same. So whatever the value I got here should be same over here within the experimental measurement and within the experimental error. I will tell you one thing. Whatever the measurement you make, without the knowledge of uncertainty, without the knowledge of error in the measurement, that experiment is meaningless. So that's why I got the knowledge. I'm going to predict something. This might be my extra time. When I measure the time period, I may get extra 0.1 or I can lose 0.1 second. So I cannot get better than this 0.1 error. And also, the length. Also, if I measure the length from here to here, as it is, it's of 50 centimeter, it's a half meter. So I have to be very, very, very accurate in measurement of length. So I may lose a fraction of millimeter while measuring the length. That should be counted as well. Now, so I'm going to measure what is the time period for one oscillation of 50 gram mass. I'm not going to cheat you. I've got a time clock over here. So what I'm going to do is to make my measurement very well, to just reduce error as possible as I can. I'm going to give 10 oscillations. I'm going to calculate what is the time period for the 10 oscillation. First for 50 gram, and also I told you that the amplitude doesn't matter from where I leave this bob. And so this is a main position. This is maybe now extreme position for the time being. I'm going to leave. So very smoothly oscillating. I'm going to count what is the time taken for the 10 oscillation. So I'm going to show you this also. So now let me start. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 14 seconds, 35 milliseconds. I got the time period for 50 gram is 14.35, and that is for 10 oscillation. But I want what is the time period for one oscillation. That is 1.435 seconds within the experimental error. Now next, I'm going to find out what is the time taken for 10 oscillation for the double of the mass, that is for 100 gram. Here it is. So I'm going to give a very smooth oscillation. and it's oscillating very smoothly. I'm going to start from any extreme position. It's very easy to measure the time if I start from the extreme position. Stop. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 14.72. Theoretically predicted 1.418 second. This is 1.472. That is for time taken for one oscillation. For 50 gram, 1.435. For 100 gram, 1.472. Both theoretical and experimental value are fantastic, agreeing each other. Fantastic, there's a great agreement between this theoretical value and the experimental value. This is how physics works.